Questions 8 through 10 on the 2002 Grade 12 Euclid Math Contest. In a soccer league with 5 teams, each team plays 20 games, that is 5 games with each of the other 4 teams. For every team, every game ends in a win, loss, or tie. The number of wins, losses, and ties for each team at the end of the season are shown in the table. Determine the values of x, y, and z. So I'm just going to concentrate on Team E, since that is where x and y and z are located. They have the following numbers: x, y, and z for wins, losses, and ties respectively. And they want you to figure out those values. Now look at the table. For Team A, for example, the number of wins, losses, and ties equals 20. And that makes sense because they played 20 games. Same thing with B. 7 plus 9 plus 4 is 20. And exact same for C and D. So therefore, X, Y, Z must also add up to 20. So that's the first piece of information that we can come up with from the question and the diagram, the table. Anything else? Well, how about if we look at the fact that all of the wins and all of the losses. So look at the entire table and look at the win column. Let's add up all the wins. 2 plus 7 plus 6 plus 10 plus x. So all the wins are going to be 2 plus 7 plus 6 plus 10 plus x, like that. And that is 25 plus x. Correct? And similarly, I want to add up all the losses. So that will be 15 plus 9 plus 12 plus 8 plus y. And the number of losses in total is 44 plus y. Now think about this for a second. The total number of wins and the total number of losses have to be equal to each other, right? Because when a team plays, it has to be either a win or a loss or a tie. Now, if it's a tie, those are all basically put in a separate category, which is right here. But the wins and losses have to be equal, because in any game, if it's not a tie, it will be one team wins and one team loses. So the total number of wins has to equal the total number of losses. So keeping this in mind, we can equate these two. 25 plus x is equal to 44 plus y, like that. And this gives us, if we isolate, x minus y will be equal to 19. So there you have it, this one and this one. Unfortunately, we have 3 variables and only 2 equations, so we have to do a little bit of inspection here. All right, no problem. Let's use inspection. Now, before I start plugging in values of x and all that, look at this equation right here. X minus y is equal to 19, right? What is the maximum value of x? X represents the number of wins for Team E. They play 20 games. So how many wins can they have? Well, X maximum value is 20 if they win all their games. And what's the minimum? What is the boundary for X? Looking at this equation right there. Well, X minus y is 19, right? So X must be at least 19. Because think about it, if X was 18, then you would get a negative value for y. If X was 18, for example, and you plugged 18 into there, you get y is equal to negative 1. But y represents what? The number of losses, right? For Team E, you can't have negative 1 losses. That wouldn't make any sense. So these are our boundaries for x. And that's very helpful because we then therefore only have to plug in 2 values for x to figure out what z can be, and then therefore what x and y can be. So let's do that. First, let's start with x equals 20. If x equals 20, that means 20 minus y is equal to 19, and therefore we have y is equal to 1. Now let's look at this equation to figure out z. We have 20 plus 1 plus z is equal to 20. And therefore, it looks like 21 plus z is equal to 20. So therefore, z is equal to negative 1. And z represents the number of ties. You can't have negative 1 ties, right? So that's no good. So x is not 20. So no problem. We can keep moving forward here. How about the only other possible value for x, which is 19? Let's see what that gives us. If x is 19, we have 19 minus y is equal to 0, and therefore y is 0. How about z? Using this equation right here, 19 plus y, which is 0, plus z is 20, and therefore z is equal to 1. So there you go. This all makes sense. So x, y, z is 19, 0, and 1. Team E wins 19 games, has 0 losses, and has 1 tie. Prove that it is not possible to create a sequence of 4 numbers a, b, c, d such that the sum of any 2 consecutive terms is positive and the sum of any consecutive 3 terms is negative. So we have a, b, c, and d. And let's talk first about their first condition. The sum of any 2 consecutive terms is positive. So that means that a plus b is positive. Any 2 consecutive terms is positive. So that means either a plus b is positive, b plus c is positive, or c plus d is positive. That's the first condition. And then the other one is the sum of any 3 consecutive terms is negative. So that means a plus b plus c is less than 0, or b plus c plus d is less than 0, like that. Okay? Now, where do we proceed from here? We have to show that this is not possible. Okay, let's see. Well, the only thing I can think of is adding them. If you add all of these, you get a plus b plus b plus c plus c plus d. And obviously, that's greater than 0. 3 things that are greater than 0 all added together. If you combine, you get 2b, 2c plus d. Okay, this is about as far as I can go. Same thing over here. Let's add these. A plus b plus c plus b plus c plus d is less than 0. 2 things that are less than 0, if you add them together, they're going to be less than 0. And then if you combine these, you get a 2b plus 2c plus d is less than 0. Now take a look at these 2 expressions. This part and that part are identical. In the first one, we're saying that a plus 2b plus 2c plus d is greater than 0. And in the second one, we're saying a plus 2b plus 2c plus d is less than 0. Well, both of these can't be true, right? Both can't be true. And therefore, a contradiction exists. So since we have a contradiction, that means that no such sequence A, B, C, D that meets these conditions can exist. And there you have it. We've proven by contradiction. In triangle ABC, ABC is 90 degrees. Rectangle DEFG is inscribed inside ABC triangle as shown. Squares JKGH and MLFN are inscribed in triangle AGD and triangle CFE, respectively. If the side length of JHGK is V and the side length of MLFN is W, and DG is equal to U, prove that U is equal to V plus W. So we need to label a lot of things here, but not too many. the first thing is this square JHGK. JHGK is a square, according to their question, and its side length is V. So this is V, this is V, this is V, and this is V. And then MLFN, another square right here, MLFN, that has a side length of W. So this is W, 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 and like that. And then DG is U. So this whole thing right here is U, top to bottom. I'll put a big U there, like that. And anything else? I think that's it. That's all they give us. Oh yeah, they give us that this is a right angle. Maybe that'll help us. And they want you to prove that U is equal to V plus W. All right. So where do we go from here? It's number 9 and late in this Euclid exam, so although there's no 100% guarantee, the fact that they've given us an angle makes me think of trigonometry. So I'm going to proceed in that direction. Euclid exams love trigonometry, especially late in the contest. So let's label this angle right here. This guy I'm going to call theta. All right? And since this is a square, this side is parallel to that side. So therefore, this angle will also be theta. I'm going to squeeze that in there, theta. And very similarly, that side, DE, is parallel to the bottom. So that will also be theta. I hope you are convinced of that. Okay? So those are all thetas there. And then if you look at this triangle right here, this cap, I guess, the snow cap at the top, that has angles of theta and 90, so therefore this must be 90 minus theta. There we go. Okay. And this is obviously a rectangle, this shape DEFG. They even tell you that, actually. So I didn't have to say probably a rectangle. It is a rectangle. And therefore that is a right angle right there. And since this angle is 90 minus theta, this angle must be theta. Now you say, well, how do you get that? Well, because remember, all the angles about a line are equal to 180. So 90 plus 90 minus theta plus theta has got to be 180, and it does. Okay? You can do that on the side if you're not convinced. So this is the setup of the question. The setup is actually not that difficult, but to come up with this on your own on a math contest, it is challenging, I think. It's easy when you look at the solution, right? And I've always said that, but you've got to be able to do this on your own under the pressure of time on a math contest. Now, let's proceed with trigonometry. Now, which trigonometry expression do you want to use? You want to use sine or cos or tangent or what? And another question is where? If I choose sine, which triangle am I going to put sine on, or cosine? Well, I'll give you the first clue. We're going to use tangent, tan of something. And before I tell you the triangle, I'm not trying to create suspense. I have to label something before I tell you which triangle. I have to label this side right here, from D down to that point. Okay? Now, from D all the way down to G is U, right there. They even tell you that DG is U. And H down to G is V. That's just the side of a square. So that means that this red line that I wrote has to be U minus V. Okay? That's just simple subtraction. And now I'll tell you that the triangle that we're going to concentrate on initially is this one right here. This triangle right there, DJH. So on triangle DJH triangle, the tan of theta is equal to, you tell me, what is it? Opposite over adjacent, correct? So opposite is U minus V. over adjacent, which is v. All right? So that's our first equation. The second equation is also going to involve tangent. But which triangle am I going to focus on now? I'm going to focus on this one right here, ENM. And very similarly, I have to figure out this segment, this line segment. What is its value? Well, from top to bottom, from E to F, that whole thing right there is U, correct? Because it's the same as DG in terms of its length. And from N to F is W. So therefore, E to N is U minus W, like that. So therefore, now going back to our tan, the tan of theta, this theta right there, using that triangle, ENM, triangle ENM, the tan of theta will be opposite, which is W, over adjacent, which is U minus W. All right? So I hope that makes perfect sense to you. No tricks, nothing fancy. Now, tan of theta, we have two expressions for tan of theta, and therefore they must be equal. So U minus V over V has to be equal to W over U minus W, like that. Okay? I think we can squeeze this in. Cross multiply, you get U minus V, U minus W is equal to VW, correct? Multiply this out, U squared UW, VU minus VW is equal to VW. This is plus. The VW's on both sides disappear, so you're just left with U squared minus UW minus VU is equal to 0. Factor out the U, and you'll get U minus W minus V. And therefore, if we divide both sides by U, all we're left with is U minus W minus V is equal to 0. And our final step, put the W and V on the other side, and you get U is equal to W plus V. And guess what? That is what they wanted you to prove, that U is equal to V plus W. So there you go. You just proved it. Three thin metal rods of lengths 9, 12, and 15 are welded together to form a right-angled triangle, which is held in a horizontal position. A solid sphere of radius 5 rests in the triangle so that it is tangent to each of the three sides. Assuming that the thickness of the rods can be neglected, how high above the plane of the triangle is the top of the sphere? So first thing we've got is these rods, right? They're fused together to form some sort of a triangle like that. And the good news is that they tell you that it is a right angle. So let's make that the right angle. And then they place a sphere inside. So I'm going to try to draw that. So here you have a sphere, and around it is a right triangle, and I hope you can visualize this. It's kind of difficult, I know, but what I've done is I've drawn it in a way so that these solid red lines represent the triangle that you can see, and then the thinner red lines are what you shouldn't be able to see. It's on the other side of the sphere, and at some point we have this intersection. And now what they are saying is that they are telling us that the radius of the big sphere is 5. And somewhere in this sphere, there is going to be a point that, if you look at it from a perspective of a horizontal plane, it's going to cut the sphere, all right? And from that point to the top, very top, they want you to know what is the distance. So let's say it cuts it, it's hard for me to draw, but let's say it cuts it here. They want you to figure out the distance from the very top till that point. All right? So I hope that makes sense. Now, the very first thing I have to do is make that cut, that cross section. To picture it like this is a chocolate ball, something that you can cut, and you're slicing it. You're slicing it exactly right there where that line is. And I'm going to now look at that cross section. And that diagram represents the cross section. So I really want you to understand the question before I move forward. You've got this sphere, right? And somewhere they have sliced this sphere about here, basically, that area right there. It's obviously below the center of the sphere, because if you chopped it at the center, then it would basically become half of a sphere, and that's not what we have. We have it a chop that is basically, or slice below the center. You understand? And then therefore, when you create this cross section, this blue section here is basically looking at it from the bird's eye view of the sphere once you've sliced it. All right? So now what I'm going to do is I'm going to label the center to the tangent lines like that. From there to there, from there to there, and from here to here. All right? Now these represent the radius of that blue circle, right? Now, please remember that this radius is not the radius of the sphere. It is just the radius of that blue circle. And that blue circle is just a cross-sectional area of that slice. Okay? So now we need to draw a few more lines, and I will then start explaining this. The next few lines are basically from the center of the circle to the edges of the vertices of the triangle, like that. Okay? And then we start labeling what they gave us, the side lengths of that right triangle: 9, 12, and 15. Okay? And 9 squared plus 12 squared is equal to 15 squared, so that's why we know for a fact that it's a right triangle. Now, the full area of this triangle, since this is a right triangle, is going to be 1/2 9 times 12, correct? 1/2 base times height, basically. And also, if you look at this diagram, if you were to add up these guys, 3 triangles, if you add them up, it would equal the full area. So the 3 triangles are this one here, right? That's the first one. Then you add it to this guy, and then you add it to the bottom one, this one right here. If you add up those 3 triangles, it should be the same. And we can do that because we have length, we have the height of all of those. So for example, for the first one, which is right here, it's basically 1/2 base times height. The base is 9 and the height is r, correct? And then similarly for this guy here, length and height of that triangle, 1/2 base is 15 and the height is r. And finally, in that triangle, we have the base and the height. 1/2 base is 12 and the height again is r. So we can do this now. 12 divided by 2 is 6. 6 times 9 is 54. Like that. This becomes 9 over 2r plus 15 over 2r plus 6r. So this becomes 24 over 2, which is 12r plus 6r, so 18r. And therefore r is equal to 3. So this r is 3. And I hope now you know that it's not the radius of the sphere, because the radius of the sphere is 5, correct? All right. Now let's start talking about what is it that they want us to figure out. This point right here is basically where the slice happened, okay? So somewhere. It's a 3D diagram, so I know it's a little bit hard to visualize, but just be convinced of that. that the slice happens here. All right? And they want you to figure out how high above the plane of the triangle is where the slice happens, is the top of the sphere. So basically from this plane all the way to the top, what is that height? So we'll label it something. Let's call it H. Okay? Like that. Now I'm going to draw it again because I really want you to be convinced of what is happening in this question. I want you to really understand it. So here we go. There's that cross section again. And there's your blue circle that represents the cross-sectional area. And we calculated this R right here is 3, correct? And then now we want to figure out the distance from the plane, which is right here, all the way to the top of the sphere, which is right there. Now we know that as we get up to there, there's going to be a radius, correct? There's going to be a radius. So I've drawn that in. Radius of what? Radius of the sphere, which is 5. And then this C that I drew represents the center of the sphere. And then from the center of the sphere down to the bottom or down to the plane is this distance right there. All right? And that distance I can call H. And that's pretty much it. And now I'm going to draw one final line, and that is a line from C to the edge right there, like that. And that line that I drew, because it's from the center of the sphere to a point on the edge of the sphere, that represents the radius. All right? And this in here is a right angle right there. So, without getting too messy, we can always redraw this to make it a bit clearer. This triangle that I drew in there, right there, like this. Okay? So what do we have here? We've got, this is a right angle. This is 3, this is H, this is the center point, and this is the radius. All right? And we can use Pythagoras. 3 squared plus H squared is equal to R squared. And therefore H squared is equal to, R is 5, so 5 squared minus 3 squared. 25 minus 9 is 16. And therefore H is equal to 4. So H is 4. And we're done. We want to know the distance from the plane of this triangle, which is right here, all the way to the top. Well, from here to here is 4. From here to here, the center to the top is 5. So therefore the total distance is 4 plus 5, which is 9. The top of the sphere is 9 units above the plane of the triangle. A triangle is called Heronian if each of its side lengths is an integer and its area is also an integer. A triangle is called Pythagorean if it is right-angled and each of its side lengths is an integer. Show that every Pythagorean triangle is Heronian. So first we've got some triangle. We don't know what its lengths are, but it's some triangle. It's not a right triangle necessarily. And it's got side lengths A, B, and C. But we know, according to the definition of Heronian, that A, B, and C are integers. Correct? And the area of this triangle is also an integer. So this is our Heronian condition. So I'll write H for Heronian. And then our Pythagorean conditions are somewhat similar but not identical. You've got a right triangle this time, like that. And we have, let's say, A, B, C. Our conditions now are that it's a right angle, which we have wrote in our diagram. And the side lengths A, B, C are integers. So there you go. Now, what they're saying in part A is that show that every Pythagorean triangle, so every triangle like this, is also Heronian. Now, how do you do that? Well, let's see. Look at our definitions. Pythagorean means right angle and ABC are integers. Heronian, ABC are integers and area is an integer. So what is common in this is that they're both have integers as side lengths. But if we want to show that P, Pythagorean triangle, is also Heronian, we have to show that its area is an integer. If we can do that, then we will be able to show that the Pythagorean triangle is Heronian. And in our case, every Pythagorean triangle is Heronian. Correct? All right, so let's move forward with that. We've got to show that this Pythagorean triangle has an area that is an integer. So our first relationship, of course, is that a squared plus b squared is equal to c squared, correct? And then area of this triangle is 1/2 base times height. We'll let b equal the base, and the height we'll let a equal the height. And therefore this becomes a times b over 2. We have to show that this is an integer. A times b over 2 is an integer. So how do we do that? We have to show that it's always an integer, because every single one of these Pythagorean triangles has to be shown to be Heronian, and therefore we have to show that the area is always an integer. All right, well, we can use basically the only two things we have. We only have this relationship and we only have this expression. So the way to approach this is by looking at odd and even. Odd and even. We have to see, is A odd, is B odd, is A even, is B even, like that. Okay? So the first thing I'm going to do is let A and B, both of them, be odd. And let's see if this works. So that means A would be like 2m plus 1, right? That's how you write an odd number. And B will let it equal 2n plus 1, like this. And let's see what we get. So using our Pythagorean relationship, we would basically get the following. 2m plus 1 squared plus 2n plus 1 squared is equal to c squared. But instead of c squared, 2k for c. Why? Because if both a and b are odd, and a squared plus b squared is equal to c squared, c must be an even number. Like, you can try it. Let's say you had 7 and 7 as your two odd numbers. If you take the square of this and add them, it becomes 49 plus 49, which is an even number. If you take two odd numbers and square them and add them, the result will be even. So that's why I put 2k for c. So let's multiply this out, and we got 4m squared plus 4m plus 1 plus 4n squared plus 4n plus 1. And this is 4k squared. All right? So let's see what we have here. We've got 4, being able to factor that from quite a few terms here. Plus n, like that, plus 2, and this is equal to 4k squared. All right, so that means that this number is a multiple of 4, and this is also a multiple of 4 right here, up until there, because you've got the 4 in the middle. But then you're adding a 2 to it. If you add a 2 to a multiple of 4, it will not be a multiple of 4. You would have to add 4. So this expression essentially cannot happen. It's a contradiction. So that basically means that A and B both cannot be odd. A and B both can't be odd. All right? So that means at least one of them has to be even. So let's proceed. At least one of them has to be even. So let A equal the even number. So if A is even, we've got 2m for A. All right? And B is some integer. Now let's look at the area. Area is always 1/2 base times height, which is the expression that we had up here, right there. If we're putting in an even number for A, we basically get 1/2 times 2m times b, which becomes mb. And this is always going to be an integer, because you're just taking an integer b and multiplying by another integer. Let's do it for b. It would be the same thing. Let b equal the even number, and then a is just an integer. Very similarly, 1/2 base times height will be 1/2 base times the height, which is b, and this becomes a times m, which is also always going to be an integer. By letting at least one be even, our area will always be an integer. And therefore, we have proven that in a Pythagorean triangle, the area is always an integer. And therefore, all Pythagorean triangles are indeed Heronian. So that takes care of 10a. 10b, show that every odd integer greater than 1 is a side length of some Pythagorean triangle. So A, B, and C, correct? We've got Pythagorean triangles that have right angles. And if this is your right angle, and this is A, and this is B, and this is C, A squared plus B squared is going to be equal to C squared, right? We all know that. So every odd integer greater than 1 is our criteria, is a side length of some Pythagorean triangle. So all our odd integers greater than 1 are 3, 5, 7, 9, like that, right? And you can figure this out. Some of these you probably have memorized, like 3, 4, 5, 5, 12, 13, 7, 24, 25, 9, 40, 41. And we have to show that this is always possible. Anytime you choose some odd number, and we'll let the odd number be, say, 2k plus 1, this is always going to be possible. You're always going to get a B and a C that fulfill this relationship. All right? So for B, I don't know what B is. If 2k plus 1 is A, I have no idea what B is, so I'll just call it B. Right? But C, I hope you can notice by looking at these, and you can keep doing this to show that C will always be 1 more than B. Right? So that means C is equal to B plus 1. Okay? And then now we have to then plug in these numbers and see what we get. So plugging in 2k plus 1 as A, B is just B, and then C will be B plus 1, like that. All right, let's expand and see what we get. So we got 4k squared plus 4k plus 1 plus b squared is equal to b squared plus 2b plus 1, like that. The b's cancel, the 1's cancel, and then we've got 4k squared plus 4k is equal to 2b, correct? Divide through by 2, 2k squared plus 2k is equal to b. So that means that b, you can always get some number for it. All you have to do is just put k into this expression. So this can always be done for any k, where k is 1 or 2 or 3 or 4 and so on. All right? And therefore C is just b plus 1. So if b is 2k squared plus 2k, you just add an extra 1 and there you got c. All right? So that's really all they're looking for in part B. Now let's turn our attention to the final one, 10c. Find a Heronian triangle which has all side lengths different and no side length divisible by 3, 5, 7, or 11. So let's first list our Heronian or possible lengths, right? Starting with our Pythagorean relationships, because in part A, we showed that Pythagorean triangles, every Pythagorean triangle is also Heronian. So if we start with Pythagorean triangles, we're essentially talking about Heronian triangles. So we've got 3, 4, 5, that's a Pythagorean. I'm just going to go off the list. 6, 7, 8, 9, 10, 11, and let's see. And these are, like I previously mentioned, either triangles that you've memorized or triangles that you can easily get from what we did in part B. Part B essentially allows us to figure out a lot of these with those formulas that we came up with. Remember, with the K's? And I'm just going to list a few of these. All right? And all of these, as you know, satisfy our Pythagorean relationship, which is that A, B, and C, if they are the lengths of the triangle, then a squared plus b squared is equal to c squared. And all Pythagorean triangles are Heronian. We proved that in part A. So we're going to use Pythagorean triangles to find a Heronian triangle using this criteria. And the criteria is that you've got to find one that has no side length that's divisible by 3, 5, or 11. Now, the key to this question is to understand the following, that if you have two Pythagorean triangles and you join them together, they will also be Heronian. Now, why is that? Is there just something I just pulled out of nowhere? Or is there some rhyme or reason to this? Well, just think about it for a second. Here's two triangles that are right triangles, and I'm joining them together. So here's one and here's another one, right? And these are, let's say, both Pythagorean triangles. If they are, that means that we have integer side lengths, right? And we have right triangles. So exactly what it says up there, right angles and integer side lengths. Now look at it from a whole, the entire triangle. The entire triangle will also have integer side lengths. And since you have A, let's say B, C, and then some other numbers D and E, and A and B are integers, if you'd figure out the area of this, which will be basically 1/2 base, which is A plus D, times height, which is B, this will equal an integer. And therefore, it will be a Heronian triangle. And that's because at least one of these is even. At least B is even, or the sum of A plus D is even. And we showed that in the previous part of the question. I believe it was part A. So this is what we're going to work with to figure this out. So here we go. So now let's go through what we have and let's try this one at a time. Can we choose 3? Well, no, because side lengths can't be divisible by 3, 5, 7, or 11. So 3 is gone. Can't use that. Similarly, we can't use this because it's divisible by 5. Can't use this because 6 is divisible by 3. 7 is divisible by 7. How about 8? 8 is not divisible by any of these. So I'm going to first try this guy, this triple, and let's see what we get. So I've got two right triangles that I've fused together, and I'm going to use this guy right there. And let's see, if I put them in, I'll put this as 15, I'll put this as 8, and this as 17. And I'm going to put them on both sides. So this is 8 and this is 17. Now, In this triangle, are any of the sides divisible by 3, 5, 7, or 9? This side looks like it's 16, that's 17, and that's 17. So no, none of them are. But here's the problem. We want all side lengths to be different. In this one, this side is the same as that. So we've satisfied half their criteria, but unfortunately we didn't satisfy all the criteria. This is indeed a Heronian triangle because all the side lengths are integers, and that the area is also going to be an integer, right? Because the area is going to be 1/2 base, which is 16 times 15, and this is basically 8 times 15, and 8 times 15 is an integer. So it satisfies the criteria of Heronian, but in C they've added an additional criteria that the side lengths must all be different. So unfortunately, that triangle doesn't work. All right, no problem. Let's move on. Let's go back to our list here and see. 9, can I use 9? No, because 9 is divisible by 3. That's no good. How about 10? Well, 10 is divisible by 5, so that's no good. How about 11? Well, 11 is divisible by 11. But this is the part of the question that is probably the most challenging. We can still use this. Why? It doesn't satisfy, right? You can't have a side divisible by 11. That is correct. But if we put these numbers into the shape in a way, we can make it so that the entire side is not divisible by 11. And that is probably the most challenging part of this question. And a diagram will explain what I mean. So again, I've got two Pythagorean triangles that I've fused together. And I'm going to use these two. I like this guy here because I came close. And this seems to be the only other one that perhaps will give me something, as long as I don't make 11 an entire side. So I can't put 11 here or 11 here, but I can put 11 here, because 11 plus this will be the side length, and therefore that side will not be divisible by 11. So let's put 60 here. Why? Why don't I put 60 here? Well, because a side length cannot be divisible by 5. So if you put 60 there, it'll be divisible by 5. But if I put 60 in the middle, that's not a side length, and therefore 61 goes there. So far, all side lengths are not divisible by any of these. All right, so far. Now, what about the other sides here? What can I do? Can I put the same 11, 60, and 61? No, because then we're going to run into the same problem we did up here, that we're going to have two sides that are exactly the same. So here is the, I guess, the magical part of this test question, is that you put in this guy right here, but you put a multiple of that. So you can't put 8, 15, 7, right? That won't match. But you can put a multiple of 8, 15, 7. Multiply this by 4, this whole thing, and that would make it 32, 60, and 68. 60 being common right there. And then 32 and 68, where do you want to put the 32? Where do you want to put the 68? You have to put the 32 here and the 68 there. Now let's see, does this fit all the criteria of a Heronian triangle? Let's look at it. First of all, side lengths are all integers? Yes, indeed. Then area is also an integer? Well, let's see. The area would be 1/2 base times height. 1/2 base is 43 times the height, which is 60. And this looks like 30 times 43. And that is definitely an integer. So those criteria are satisfied. This is indeed Heronian. Now let's go to the criteria of 10C in particular. Are all side lengths different? Right here. And the answer is yes. 61, 68, and this side length is 43. 43. And no side length divisible by 3, 5, or 7. 61, 68, and 43. None of those are divisible by 3, 5, 7, or 11. So there you go. It's a challenging question. It's more of a puzzle than a question, but that is the Heronian Triangle. It's a triangle with side lengths 61, 68, and 43.